Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 1 for June 2022. This is the Part 2 video. I will put the link to the Part 1 video as well as that of Part 3 below the description box. Let us begin with question 19. It says, here they say the element iron forms two chlorides. They've given us iron 2 chloride, which we have there, and iron 3 chloride. And then they say a known mass of iron powder, this should be the solid, is added to 200 centimeters cubed of a hard solution of iron 3 chloride with a concentration of 0.5 mole per decimeter cubed. That statement means that the iron 3 chloride has this concentration and that volume. When the reaction is complete, the solution only contains iron 2 chloride. This means all the iron 3 chloride is finished. Therefore, we can be able to find the number of moles of the iron 3 chloride used using exactly that volume as well as that concentration. So the question goes on to say, the unreacted iron is filtered, dried, and weighed. So the initial mass of the iron powder was that, and the final mass of the iron powder was that. So if we get the difference between these two, we can be able to find the mass of iron that reacted. So here the first question asks, calculate the number of moles of iron that react. Number of moles of iron that react should be the mass of iron divided by the molar mass of iron, or I would say the atomic mass of iron. Mass of iron divided by the atomic mass of iron. So to get the mass of iron, it's going to be that minus that, which gives us 2.79 grams. When you divide through by the atomic mass of iron, it's going to be 55.8, so we get 0.05 moles. These were easy 2 marks to get. The next part says calculate the number of moles of iron 3 chloride that react. You want to find the number of moles of iron 3 chloride, you have to refer back to the information given. They told us all the iron 3 chloride reacted because after the reaction, the only solid that was present there was the unreacted part was just iron. Remember, they said the solution only contains iron 2 chloride. That is the final product. So it means the iron was not, the unreacted iron was not in solution. So because they say solution, it means the solution did not contain iron 3 chloride. So it had reacted at all and was completed. So here the number of moles should be the concentration we were given of iron 3 chloride initially times the volume of iron 3 chloride we were given initially. I divided through by 1000 because that volume should be in decimeters cubed. So when you multiply the two, these are the number of moles you get. The next question says use your answers to A1 and A3 to write an ionic equation for the reaction of iron with iron 3 chloride. They want it to include state symbols, and you must show you're working. So to do this, I went back to the mole ratio. Because remember, according to the equation, they said iron reacted with iron 3 chloride to give you iron 2 chloride as the only product, like that. So I need to find the mole ratio to see how, in what ratio did these two react. Since I have the number of moles of that and that, when I got the mole ratio, it was 1 to 2. So that means this should be 1, that should be 2. It means this one here should have a 3 here to make the number of chlorine 6, chlorine atom 6 in total, and the total number of ions to be 3. So if you can balance this equation in this state, and you remember iron 3 was a solution, so it should be aqueous. The iron was a solid, and the iron 2 is in solution, so that is also aqueous. So we can be able to break down the aqueous. So remember when you're trying to write the ionic equation, the aqueous have to be separated, kind of like a fragmentation, but you leave the solid, you leave the liquid, and you leave the gas, but the aqueous have to be broken down into ions. So I broke this into ions. This is going to be 2. That times that gives you 6. That remains as it has been, and this one here should be 3 iron, 2 plus, and then 6 Cl minus. We cancel out things that are similar, which is that, and all that is left is going to be that plus that gives us that. This is the ionic equation that you were looking for, and therefore it should be your answer. B. The concentration of the solution obtained in A is increased by heating it gently to remove some of the water. The solution is allowed to cool, and pale green crystals of a hydrated iron 2 chloride. Here, this is the formula of the hydrated 2 iron chloride form. Analysis shows that these crystals contain 28.1 by mass of iron. Calculate the number of moles of water crystallization, X, per mole of hydrated iron 2 chloride. So here, I tried to write this it's not required to write this, but it's just for me who I wrote that. So I say let the molar mass of that be y. Remember, if you're finding percentage by mass of something, it should be the mass of that specific thing divided by the total mass times 100. So if this is the percentage by mass of iron, it should be 28% is equal to the mass of iron. In this compound here, iron should be 55.8 divided by the total, which should be the molecular mass. We do not know that. Or say the formula mass, we do not know that, times 100. So I know that, and that. I'm looking for this. So I make y the subject, and this is going to be 55.8 divided by 28.1 times 100, and I get 198.58 gram per mole. This is the molar mass, which is y. Remember, the question is asking you to find the number of moles of the water of crystallization. So since I know the molar mass of the whole thing, I need to subtract the mass of this, and I'll be able to find the mass of this thing. Since I know water is 18, this thing is going to be 18x, and I will get this. I can subtract everything from that, and I'll be able to get the answer. So I said the molar mass of this whole thing should equal to 198.58. Since this iron is 55.8, 2 chlorines are each 35.5, and the water is x, so 18x is equal to that. When I added this one, I took it the other side or subtracted from this one, I got 18x is equal to 71.78, and x is equal to 3.988. However, this should be a whole number, so rounding it up, it becomes a 4. Therefore, the value of x should be a 4. So that is the end of question 19. Let's continue to question 20. And again, to do this, remember they asked you to calculate the number of moles of the water of crystallization x. So x was 4. Moving on to question 20, let's see. Here they say naturally occurring bromine has 2 isotopes. There is bromine 79 and bromine 81. They ask you, state what is meant by the term isotope or isotopes. Isotopes are atoms of the same element that have the same atomic number but have different mass numbers. So if you include same atomic number, different mass numbers, that is going to be a perfect definition. The next part says complete the table to show the numbers of subatomic particles in the 2 isotopes of bromine. Subatomic particles are particles that are found within the atom. They include electrons, neutrons, as well as protons. So in bromine 79, the number of protons is 35. Remember, bromine has atomic number 35, so whether it's bromine 79 or bromine 81, both have the same atomic number. Therefore, they have the same number of protons. Now, for bromine, for number of neutrons, the number of neutrons are going to be the mass number here minus the number of, I would say, protons. So the difference between these two is going to be a 44, and the difference between these ones here is going to be a 46. So the number of electrons, since they are both atoms, that number of protons and the number of electrons has to be the same. If there were ions, then the number of protons and electrons will be different. So in this case, they're all atoms, so protons and electrons are the same. Moving on. Here they say the mass spectrum of a sample of bromine is obtained. Draw a dot and cross diagram to show the bonding. In a molecule of bromine, only the outer electrons should be used. Now here, I used different electrons that I used a dot and cross diagram. Some people will use dot and dot, but since they say dot and cross, I stuck to dot and cross. So bromine, each bromine has 7 electrons in the outer shell, which is 1, 2, 3, 4, 5, 6, and a 7th. And on the other side, there's 7 as well. So they share a pair of electrons between them. When each electron is contributed by one of the atoms in this specific covalent bond. So drawing it like this could earn you the marks you're aiming to get. So moving on here, they say, describe the formation of the molecular ion of bromine in the mass spectrometer. They want you to include an equation. Set symbols are not required. So remember, this is in a mass spectrometer. We are trying to find a molecular ion. A molecular ion, it means there is a molecule, meaning in the case of bromine, they are 2 atoms. So to form a molecular ion, there is going to be of course, an electron is going to be knocked out of the bromine ion, or in this case, bromine molecule of bromine, to form an ion, as we can see here. I want to re-emphasize on that. We have bromine. A beam of electron is going to be shown on so many bromine molecules. So one of the bromine molecules can be hit by an electron, and then on the other side, it becomes a molecule of +1 charge. That is going to be an ionic or molecular ion. This is a molecular ion. Still a molecule, but an ion state. And then 2 electrons. These 2 electrons here, one is the incoming electron, and the second one is the electron that has been knocked out of one of these atoms in the Br2 molecule. So this is what you would say. So I said, during ionization, in this case, a high energy electron strikes the gaseous bromine molecule, knocking an electron out. This creates an ionized bromine molecular ion. Remember, it's still going to be a molecule, but it's going to be charged in this case. So moving on, here they say on the mass spectrum, gray draw the peak of bromine molecular ions, showing the relative peak heights. So here I showed, remember they are telling us bromine 7979, bromine 7981, and bromine 8181. These are going to be in the ratio of 1 to 2 to 1. So whichever height you chose, you have to be sure it's going to be in that specific ratio. So for me, I chose to use a 40 by 80 by 40 because maintaining a 1 to 2 to 1. Another person could choose to use a 50, a 100, and then a 50. The key thing is you have to stick to the same ratio because of the abundance. The abundance here is going to be a ratio of 1 to 2 to 1. So relative abundance is like that. You have to stick to through the heights of your peak have to be exactly in that same order. So if you had done like this or use a ratio 50, 150, that will be okay as well. Moving on. Here they say the percentage abundances of the isotopes in a different sample of bromine as shown below. So let's look at this. We have bromine 79 and bromine 81, and these are the percentage abundances. And then they asked you to calculate the relative molecular mass of the sample of bromine, giving your answer to 2 decimal places. All we need to do is, it's going to be 56.38 divided by 100 times 79 plus 43.62 divided by 100 times 81. When you combine those two, you will get that, and then this is going to be the answer. So the sum of that plus that gives us, which is 79.8724. Now remember, this is just for one specific thing, but they told us calculate the relative molecular mass of this sample of bromine, giving you answer to 2 decimal places. So this is if it was just one bromine atom. Remember, in a molecule, there are going to be 2 bromine atoms. So you multiply that times 2, and then you round off to the specific 2 decimal places they have required you to do so. So finally, I got 159.74 to 2 decimal places as my answer for this. So this brings us to the end of question 20. Let's continue to question 21. Question 21. The elements carbon and silicon both form dioxides. Carbon dioxide is a simple covalent molecule, but silicon dioxide has a giant covalent structure. Describe the covalent bond between a silicon atom and an oxygen atom in the silicon dioxide in terms of the particles involved. So here we know they said particles involved. So of course, the particles involved are going to be electrons in this covalent bond. However, these electrons are being attracted by the nuclei of the atoms, meaning the silicon atom as well as the oxygen atom. So I said the covalent bond is an electrostatic force of attraction between the shared pair of electrons and the nuclei of the silicon and oxygen atom. If this is the oxygen atom, let me try to draw. If this is the oxygen atom and this is the silicon atom, this is oxygen and that is silicon. I'm just using this as a covalent bond. They are going to be sharing the electrons like that. This is an example I'm using to demonstrate. It means the positively charged nuclei are attracting the negatively charged electrons that are being shared, and that is what we call a covalent bond. The electrostatic attraction, it's electrostatic because it's between a positive and a positive nuclei, as well as the electrons involved. A positive nucleus, an electron, and the positive nucleus, an electron the other side. So electrostatic force of attraction between the shared pair of electrons and the nuclei of silicon and oxygen. Moving on. Here they say compare and contrast the covalent bonding in carbon dioxide and silicon dioxide in terms of orbital overlap. If they say compare and contrast, it means they want the similarities as well as the differences. So to compare and contrast, the similarities are both molecules contain a sigma bond. in the silicon oxygen, let's assume, and in the carbon dioxide or carbon oxygen and carbon dioxide, this is a sigma bond, and that is a sigma bond, that is a sigma bond, that is a pi bond, that is a pi bond. So both of them do contain sigma bonds. And in those sigma bonds, the orbitals, because they told you in terms of orbital overlap, so we have to consider the orbitals. The orbitals are in end-to-end overlap. An end-to-end overlap can be between two s orbitals, as the electrons are the overlap is occurring there, or it can be between a p orbital and an s orbital, as we can see that, or it can be between p orbitals and another p orbital. So all these are end-to-end overlap. They do occur in a sigma bond. So I gave the example of an overlap that you can see here. And then the differences is in carbon dioxide, it contains pi bonds, and it contains these pi bonds. I don't know if you can see the second bond I showed you here. Here, you can see that pi bond. And in this pi bond, the orbitals are not end-to-end, they are sideways. This is a good example of a sideways overlap, and it only occurs in the p orbitals, at least for your syllabus or for your level, it only occurs in between the p orbitals. So here, p orbitals aligned sideways, and then they do overlap. So this is one example for that sideways overlap, and this is an example for the end-on overlap. So let us continue. Part B says, the shape of the carbon dioxide molecule affects its physical properties. Explain the shape of carbon dioxide molecule. Anytime they ask you to explain the shape, it means you have to say what shape it is and give a reason why that shape is the way it is. So I began by saying, you could begin by this or begin by that. So you could begin by saying a carbon dioxide molecule has a linear shape with bond angle 180, then give a reason why. So for me, I said in the carbon dioxide molecule, there are 4 bond pairs. You can see 1, 2, 3, 4. So there are 4 bond pairs of electrons and no lone pair around the carbon atom. The bond pairs rearrange themselves into a linear shape of bond angle 180 to minimize repulsion. A shape of a specific molecule is created based on how many lone pairs, how many bond pairs there are. In this case, there are no lone pairs, so the bond pairs that are present have to align themselves as far away from each other as possible, and that creates a linear structure. The reason for that is there is going to be some repulsion existing between the bond pairs of electrons. So to minimize that repulsion, they space themselves as far away from each other as possible. We cannot get this kind of shape in a carbon dioxide molecule because this means these are going to be closer to each other, yet there is no lone pair here. That cannot work. If there is no lone pair, maximum separation creates minimum repulsion, and in this case, since the structure is aligned like that, it's going to create a linear structure. Moving on, they say, explain the polarity of the carbon-oxygen bond. Remember, we are talking about polarity. Is it polar? And give a reason why. And again, here they're asking explain. It means I have to talk about what polarity exists in there and the reason why it is the way it is. So I said the carbon atom in the carbon-oxygen bond is slightly positively charged, while the oxygen atom is slightly negatively charged. I don't know if you guys know this when we do carbon, oxygen, sigma plus, sigma minus. The reason for that is oxygen is more electronegative, so these electrons in the bond are more inclined towards oxygen away from the carbon, and that creates a partial positive charge around carbon, and these electrons arriving here closer to oxygen creates a partial minus charge. So I say this is because the oxygen is more electronegative than the carbon atom. The next they ask, state whether or not the carbon dioxide molecule is polar and justify your answer. So let's see, again, the carbon dioxide molecule, we have already established its shape. We know this is partially positive, that is partially negative, partially negative. Now here, polarity is drawn towards this side, and that is drawn towards the other side. The arrow is facing the more electronegative element. Now, because these two are pulling away from each other, the molecule is symmetrical, and therefore the dipoles cancel out. That means it's not going to be polar. So I said the carbon dioxide molecule is not polar. Since the molecule is linear, the dipoles cancel out. It's linear, the more electronegative is this side, the dipoles do cancel out, and that means it's not going to be polar as a molecule. The bonds in them are polar, but the molecule itself is not polar. Here they say the structure of silicon dioxide may be referred to as a structure, a diamond structure. So they've given us the silicon atoms and we can see the oxygen atoms around them. They say using your knowledge of the structure of diamond suggests how the structure of silicon dioxide is similar to that of diamond. In diamond, we have this tetrahedral shape, whereby the carbon atom at the center is surrounded by 4 other different carbon atoms, so creating a tetrahedral shape. And we can observe the same shape here. We can see at the center we have a silicon atom and we have 4 other oxygen atoms surrounding it in the same tetrahedral shape. So I said each silicon atom is bonded to 4 oxygen atoms in a tetrahedral shape. That is why the structure in silicon dioxide and that in diamond are exactly similar. So the next part says, give a possible reason why silicon dioxide has a lower melting temperature than diamond, even though the silicon oxygen bond is stronger than the carbon bond. I'm going to use a demonstration here. This is in silicon dioxide. Let me write it here. And what we have in diamond is going to be a carbon-carbon single bond like that. They have told us that this one here is stronger, while that here is weaker. If you compare a bond-to-bond, single one-on-one, the one in diamond is weaker than the one in silicon dioxide. So the reason as to why overall we have a lower melting temperature in comparison to what we have here in diamond is, in diamond we have more bonds that are present. There are more bonds. Therefore, there will be more energy that is required to break that. So many, even if they are weaker, but so many of them, you have to they require a high amount of energy to be broken, resulting in a higher melting temperature in comparison to that in silicon dioxide. I hope this makes sense to you. So I said there are fewer covalent bonds. Let me use this one. There are fewer covalent bonds in the silicon dioxide structure than in diamond. So overall in diamond, you require a higher amount of energy to break all the covalent bonds. That is why the melting temperature is higher. So this brings us to the end of this video. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.